Hello. Today we're going to be going over a chi-test for independence. A chi-square test for independence is used when you have two nominal variables and you want to see whether they're related or independent. The police are notorious for stopping cars and frisking their driver in hopes of finding contraband such as weapons and drugs. Researchers kept track of how many cars were stopped depending on car color and the gender of the person driving the car. In this example, we will be testing whether or not gender and car color are related in car stops by the police. For our frequency observed, denoted as F sub O, we have gender versus color. Our genders are man and woman, and our colors are red, white, black, and blue. The data provided says that for red cars and men, 50 people were stopped, white cars, 10, black cars, 5, and blue cars, 15. For women, 45 red were stopped, 10 white were stopped, 15 black were stopped, and 10 blue were stopped. In this example, this is the data set we have. When entering in the information, for our men, red cars got stopped 50 times, white 10, black 5, and blue 15. And for our women, 45 red cars, 10 white, 15 black, and 5 blue. The next step would be to add up these values to find our total sample size. We have 95 for red cars, 20 for white cars, 20 for black cars, and 25 for blue cars. For men, we have 80, and the same goes for women. Now that we have this data, we can begin stating our hypothesis. The null hypothesis is H sub 0, the variables gender and car color are independent. Remember that that is the basis of this test. You're testing to see whether or not they are independent of each other. For our alternative, H sub 1, it is that there is a relationship between the two variables. Now that we've stated our hypothesis, up here, we can then set the criterion for our data. First step in setting the criterion is setting our alpha level. Which will be, in most cases, 0.05. Then we have to find our degrees of freedom. To find the degrees of freedom, we use df equals column minus 1 and row minus 1, multiplying them to get our answer. For this specific chi-test, our df is equal to 3. We got this from our columns, which there are 4 of, minus 1, which gives us 3, right? And our rows, which we have 2 of, minus 1, which gives us 1. 3 times 1 is 3. Now that we have our degrees of freedom, we can find our critical chi-squared. I will now share the screen to show you the chi distribution. See here, using the df that we have already collected, which is df equals 3, we can find that our critical chi-squared is 7.81. Now our criterion is set. The next step is to solve our frequency expected, which is denoted by F sub E. For our frequency expected, we have to use this table to create a whole new table to find our chi-squared value. Let's set up our table. To find our frequency expected, we use the frequency of column times the frequency of the row, all that divided by n. We have to do this for each of our cells. To solve f sub e, we must use the equation frequency column times frequency row divided by n. For our first cell, we do 95, which is our column, times the row, which is 80, and divide by n. 95 times 80 is 7,600. We divide that by 160, and we get 47.5. Now, we have to do this for each cell in order to calculate our chi-squared value. For our white car, we do 20 times 80 divided by 160. 1,600 divided by 160 gives us 10. That one's pretty straightforward as we have simple values, and it also crosses over. Next, we'll do our black cars. In this situation, we also do 20 times 80 divided by 160, giving us 10. Moving on to the blue cars, we do 25 times 80, which gives us 2,000, divide that by 160, giving us 12.5. Luckily for us, our values are the same for no matter what row you are in. The only difference is when you're going from column to column. So, in this case, we could plug in our values just as they are, once again. Now, in calculating this should also again come out to be 160. 47.5 plus 47.5 is our 95. 10 plus 10 is 20. 10 plus 10 again is 20. 12.5 plus 12.5 is 25. 47.5 plus 10 plus 10 plus 12.5 equals 80. And since the second row is the same, it will also equal 80. And once again, our n equals 160. To be sure that you understand the process we just went through, I will go over one of these steps in finding our FE in depth. We will do this for the first cell for men with red car. So let's remember our values. 95 for our column, 80 for our row, and 160 as our n. And again, the formula is f sub e is equal to f of the column times f of the row, all divided by n. Like we said before, the f of our column is 95. Multiply that by 80, and divide that by 160. That gives us 7,600 divided by 160, giving us an f of e for man with red car of 47.5. Now that we've solved our f sub e, we can move on to finding our chi-squared value. To do so, we use the equation chi-squared equals the sum of f sub o minus f sub e squared and then divided by f sub e. That means we subtract the frequency expected from the frequency observed, square that, and then divide that by the frequency expected for each of our cells. Taking this equation, we will solve for the first set of cells. Our f observed for our first cell is 50. And for our expected, is 47.5. All of that will be squared, which then will be divided by 47.5. And that will give us the answer of 0.13157. Now, we have to do this for each of our cells because we're finding the sum. We have to remember the sum, and using each of our cells, solve for the chi-squared. I'm going to write out all of the chi-squared formulas and sum them for us so that we don't have to go through that lengthy process. Remember to do it for each of your cells. Here we have all of the equations for chi-squared written out. At the top of each equation, you will see a red value that represents the answer to each of them. We will now sum them together. 0.13 plus 0.13 plus 0 plus 0 plus 2.5 plus 2.5 plus 0.5 plus 0.5 will give us a chi-squared of 6.26. Now that we have all of our values, we can test our chi-squared against our chi-squared critical. This will allow us to make a decision about our hypothesis and overall make a decision about the relationship between gender and car color. So our chi-squared is equal to 6.26. This is our calculated chi-squared. Our chi-squared calculated is 6.26. Compared to our chi-squared critical, it is less than the chi-squared critical. Remember, our chi-squared critical is 7.81, and that represents the threshold for which we reject our null hypothesis. So let's write that out. Our chi-squared stat is equal to 6.26, and compared to our chi-squared critical of 7.81, our chi-squared stat is less. Now that we know this information, we can make a decision about our hypothesis. Because our chi-squared stat is less than the chi-squared critical, we fail to reject the null hypothesis. And to represent this in reporting, we would say the chi-squared of the degrees of freedom of 3 and a sample size of 160 gave us a chi-squared of 6.26 with a p-value that is less than that is greater than 0.05. Now that we have this information, we can discuss what that means for our data. Failing to reject the null hypothesis signifies that our data does not represent a relationship between car color and gender in police stops. Rather, they are independent. Now, that being said, that does not technically mean that they're independent. It could just mean that our data doesn't have enough information, and thus, if we got more information, we may see more of a relationship between the two. Of course, we would have to run another test to see that. The final step of hypothesis testing is seeing the effect size. Now, normally we would do this if we had rejected the null hypothesis and found a significant relationship between gender and car color or any variables for that matter. But since we didn't, we won't be doing that. Thank you so much. Have a good day.